All right. Good morning, good afternoon, ladies and gentlemen. Welcome to this series of online lessons. We are back again with my Einstein, Mr. Peter Mwani.
Good
yeah,
morning, good afternoon, viewers.
yeah. So I'm with my student, and we're just going to go through wave equations. And before we start, I'll give you like an intro to some let me say some tools that we'll be using. And I believe these tools, you covered them during your study of ordinary differential equations. Okay, so this is more like just a reminder. So use the separation of variables to solve the following PDEs. So these are partial differential equations. And we have the equation, which is the wave equation, and it is of this form. And it has these boundary conditions. So we are going to use these boundary conditions to find the final solution. And an initial condition is the starting condition. But the tools that we're going to use, first of all, is if you have a differential equation of the form y double prime plus some constant b, y equals to 0. This y could be a function of x, okay? So similar to what we've seen, okay? So this could be the 2y dx2 plus b, then y is a function of x. So this and this mean the same thing, okay? So if you have a differential equation like this, uh, you can always factor out the y, okay? So you can factor out the y. Then this is some form of differencing method, okay? So you factor out a y, and here you remain with some constant which will be squared. So you just say maybe we can use r squared plus b, okay, let me use equal to 0. Then you're going to solve these equations. So y will be equal to 0 and r squared plus b will be equals to 0, okay? Now solving for r is what we would call an eigenvalue, okay? Are you following?
Yes.
Yeah, so for all the equations, the heat equation, the wave equation, some way or another we'll run into this problem where we have to factor out some y so that we remain with some form of quadratic equation. And we can use uh, the methods that we know to solve for r. So r squared will be equals to negative b, okay? Then you have r equals to plus or minus, you introduce the square root of negative b. Excuse me. Forgive me for that. I have flu. So, yeah. So,
So fine.
yeah. So, we are here. Okay. Now, the different values of r will determine the final solution of y. Okay.
Okay.
Yeah. So now, what affects the solution of r is this b here. Okay. If b,
Okay.
yeah, you see, if b is greater than 0, what type of what number is this? To be,
It's going to be a complex number.
so r will be a complex. Okay. So let me write it here. So if b is greater than 0, r will be equal to plus or minus I some constant w. Okay, it will be a complex number. Then our method says if we have a complex number, if r is a complex number, then the solution, a complex number is made up of sine and cosine, right?
Mm-hmm.
Yeah. So meaning that the solution will be some a cos r, okay, r
Okay.
x plus b sine r x. So this will be the general solution. It means you have solved this differential equation.
Okay.
Yeah. So you take note of this because it is what we are going to be using. Remember when I first started, I showed you why we need to solve for c that is positive, negative, and so on and so forth.
Yes, yes.
So we are going to have different solution depending on whether we have a positive number, negative number, and so on and so on. So now, if b is less than 0, okay, taking this, if b is less than 0, are we going to have a real number or a complex number here?
It's going to be real.
Okay, so r is equals to plus or minus some number w, which is a real number, all right? Then
Okay.
if we have a real r, then the solution of y is equals to a e to the r1, okay, r1x plus b e to the r2 x. Okay, so remember here r has two solutions, the positive and the negative. So r is equals to plus w, maybe can be r1, and r2 can be minus w. But for the complex part, we just take the positive value. We don't take the, we just take, for instance, w here and w here.
Okay.
Okay, so this is the case. So for the complex part, we just get the w and the w, but here we get the positive part and the negative part. Then it will be like that. So there is another form if we have repeated roots, meaning that r1 is equals to r2. Okay,
Yes.
then there is also a form. So you write it as a plus bx, then you factor out e to the r1, I think should be x. But anyway, we won't look at this form, but something like that. Since r1 is equals to r2, yeah, so we would have something like that, but you can go ahead and confirm. So this is for when r1 is equals to r2. This is when r1 is not equal to r2.
Okay.
Yeah. Then the last case is if b is equal to 0. Okay?
Okay.
If b is equals to 0, the r will be equals to 0. Okay?
Mhm.
And if r is equals to 0, the solution of y is ax plus b.
Okay.
Yeah. So take note of these. We're going to be using them, these three conditions. So this will help us because from there, we can just generalize the solution. It will be much quicker because these wave equations can be longer. So I can pause for you to copy very fast. Then we can now start solving the wave equation.
Okay. I was copying as you were writing. So already done.
All right, all right. Let me just erase. All right, are you ready?
Yes, yes.
Okay, so now our wave equation is d2u dt2 is equal to c squared du dx2. Okay, so I'll do, you know that already we have to solve for c greater than 0, c equals to 0, and c less than 0, c squared, right?
Yes.
Yeah. So, but for now, I'll bring this in later. What we'll just do is we would start from the general form. Then,
Okay.
yeah. So we said, what is the general solution of the wave equation? U of x comma t is equals to what?
the general solution was okay, just give me a minute. We said it was u x comma t being equal to t t of t x of x.
Okay, t of t, then x of x. All right, so this is the general solution. Then we have to differentiate u with respect to t and u with respect to x, right?
Yes.
Yeah, so that we replace in this. So remember, this is just the same thing as u t t equals to c squared u x x, so that it's easier to write. Okay, so we differentiate here u with respect to t 2 times, so only the t part will be affected because x is acting like a constant. So u t t will just be equals to t double prime of t, then x of x. Then what about u x x? What will u x x equal to?
Okay, so the c raised to 2 will remain. Then, oh, it's this side. Okay, so we're differentiating with respect to x, so it's going to be t of t, then x double prime of x.
Yeah. So x double prime of x. So we'll replace these two equations in our original wave equation here, so that, which is the same as this one here. So we are going to have, what are we going to have? Can you give me what we'll have?
Okay, so we're replacing that with what?
We are replacing in this equation here these two variables.
Oh, okay. So where we have in u t t t, we're going to put t double prime of t, x of x is equal to c squared. Then we're going to have t of t, then x double prime of x.
Okay, good. Then here we can separate the variables. Remember, the c squared will go on the side of the t and the t like that. So here we'll divide everything by c squared t of t, and this side by c squared t of t, so that this and this cancels. And we'll do the same. So the x will come on the other side. So we'll say over x of x, and this side over x of x. Okay. Then finally, what are we going to remain with?
Okay, so we're going to remain with t double prime of t is okay. Divide by c squared t of t.
Okay.
Is equal to x double prime of x, then over x of x.
Very good. Okay. Now, for these two variables to be the same, remember, they have to be equal to some constant. We can say negative lambda squared. You can even put it as negative lambda. You can even put it as lambda. Okay. So, but for easier computation, you put it as negative lambda squared. At least for me, that works much easier. Okay. Now, remember here, all this, we're doing all this because we want to solve u is equals to x comma t equals to t of t and x of t, x of x. So basically what we're trying to find is t of t, we find t of t, we put it there, and x of x, we put it there, then we are done with solving our wave equation. Okay? Yeah. So here we can separate the variables. So we can have t, so here, so we can have t double prime of t over c squared t of t equal to negative lambda squared and x double prime of x over x of x goes to negative lambda squared. All right. So this will help us find the value of that. And this will help us find the value of that. And once we find the values, we replace there, then we solve for u. Okay? Okay. So let me start. Again, the lambda that we've introduced here, again, can be any number. So lambda can be 0, lambda can be greater than 0, and lambda can be less than 0. So we are going to do for all those cases as well. Yeah. So we have to do for all those cases as well. So it's a quite lengthy process. So that's why I thought of just showing you those equations so that it will be easier. So now here, yeah, so here we can cross multiply. So we have t double prime of t is equals to negative lambda squared c squared t of t. Okay, so we transpose, we're going to have t double prime of t plus lambda squared c squared t of t equals to 0. Okay, so we have to solve this equation. Remember, this is similar to the equation that we had in the introduction, right? Yeah, so this is similar. So same applies here. You more like factor out t of t so that here you remain with some eigenvalue r squared, since it's double prime, plus lambda squared c squared t of t. Okay, t of t. Oh, sorry, we factored out t, so it will just be like that equal to 0. Are we following?
Yes, yes.
Yeah. So here we solve for t, so we know that t of t is equal to 0, or we solve for r squared. So we have r squared. When we transpose this, we're going to have negative lambda squared c squared. Now this is where we have to do for the cases. Okay, we have to do for if lambda, okay, I'll say if c is equals to 0, then it doesn't matter what value of lambda we have. Lambda greater than 0, lambda less than 0, or lambda equal to 0. The value of r will always be equal to what?
0.
R will be equal to 0. And remember what we said, when r is equals to 0, then what is the value of t of t?
When lambda is equal to 0,
Mm-hmm.
it will be 0.
Oh, no. The general solution for y, where we had,
The general solution.
yeah.
Okay, when you are going to say y is equal to ax plus b.
Yeah, so in this case we have t, so it would be a t plus b.
Oh, okay.
Yeah, because t of t. When r is equals to 0, we're using that when the eigenvalue is equals to 0. Then we have this general form. Okay? Okay. So now, here we have kind of solved for t.
Okay.
Okay, because we have to apply the initial conditions too. So now we come to x, because we need to solve for a and b, right?
Okay.
So we'll come to it later. Come to it later.
It's a
So
very big question.
yeah, it is. It is. So imagine, so for c equals to, now we'll go for c greater than 0, then for the c and lambda greater than 0, c greater than 0 and lambda less than 0, and so on and so forth. So same applies here. We don't have c here, so this one will, so we have double prime of x is equals to negative lambda squared x of x. Okay, are you following?
Yes.
Okay, let me just see if that is in frame. Okay. Okay. So now, same applies here. Same applies here. We will bring the x double prime of x this side equal to, oh, we'll transpose, so it'll be plus lambda squared x of x equal to 0. So the same thing, we'll factor out x of x, so that here we'll remain with some eigenvalue lambda squared plus lambda squared equal to 0. So again, we solve for x of x equals to 0, and lambda squared plus, okay, eigenvalue, sorry, r squared plus lambda squared equals to 0. So again, let me move this a bit. I'll move this here. Okay, here.
Okay.
Even here, we're going to do the same thing. We
Okay.
make r squared equals to negative lambda squared. So we can get the same case when we see what the values of r will be for lambda equals to 0, lambda less than 0, and lambda greater than 0. Okay, so
Okay.
if lambda is equals to 0, we're going to have r being equal to 0, meaning that x will be equals to what?
X will also be equal to 0.
No, 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 no. We take the general solution.
Or when okay, when it is 0. So we're going to have it was ax plus b.
Yeah. So we're going to have ax plus b. When r is greater than 0, we have if r is greater than, I mean, sorry, if these are all squared, sorry, lambda squared, lambda squared. So if lambda squared is greater than 0, this part will be a positive number. Okay.
Okay.
Yeah, let me write lambda squared is equals to 0. Lambda squared greater than 0, meaning that this part will be a real number, because a positive number times negative number, it will be negative. Okay, so now when you square root that, meaning that r will be a complex number.
Okay.
Okay, and if r is a complex number, what is the general form of x?
Okay. So when it is complex, it is going to be ae raised to r1x plus be R2x.
No, that's the case when it's a real number. Remember,
Oh,
complex
that's when
numbers.
it's true.
Yeah, complex.
Okay, okay. I remember. It's y is equals to a cos wx plus b sine wx.
So in this case, it's just a cos wx plus b sine wx. Okay. Then we also take for the when lambda squared is less than 0. So when it's less than 0, meaning that it's a negative number. Okay. And if it's a negative number, there's this negative outside here. So the negative times the negative number, it will be positive. Okay. So meaning that R will just be some positive number plus or minus W.
Okay.
Yeah. Then we have x of x. When it's a positive number, what do we write?
So when it's a positive, it's what I said area, where I said it's a e to the R1x plus BE raised to R2x.
Okay, so we can put the values of R, which is negative WX plus B e to positive
E.
WX.
Okay.
Yeah. So, all right, so this gives us all the values of X for different conditions. Now, the value of T for different conditions. So I'll mark these, hope you mark them. So there's 1, 2, and 3. Okay. So we need to do the same for T. So we have, let me write down the equation for T. So we have T should be double prime of T plus C squared lambda squared T of T. And we've already solved for R. We've solved for C equal to 0, right? And for all cases. Yeah. So we are now going to solve for C greater than 0 and lambda may be greater than 0.
Okay.
C greater than 0 and lambda greater than 0. So again, we change this to an eigenvalue problem where there is double prime. We factor out T of T, remain with R squared plus C squared lambda squared. We go to 0. So again, same thing. R squared is equals to negative C squared R squared. So now we need to look at the type of number that we are going to have. If C squared and R squared are greater than 0. So if C squared is greater than 0 and lambda squared is greater than 0, when you multiply them, what type of number are you going to have? Is it going to be a positive, negative?
It will be negative.
Times the negative here.
Oh, you're saying that if they are less than 0.
If they are greater than 0. See, C squared is greater than 0 and lambda squared is greater than 0. When you multiply them, what type of number are you going to have? Positive, negative?
It's going to be negative because of the negative in front.
Okay, because of this negative, right?
Yes.
Yeah, but by themselves, this times this will be a positive number.
Yes.
Then times the negative, it becomes
negative.
Yeah. So meaning that when you check the square root, you're going to get the square root of a negative number, some number k. Okay. And what is the square root of a negative number?
It's a complex.
Yeah, so we're going to have plus or minus IW. And when R is a complex number, what is the value of T?
Okay, so it will be A cos WT plus B sine WT.
Okay, WT. Okay, that's good. We do the case. So we are finding all the values of T and all the values of X. Then we'll come and
Okay.
pair them because we'll need them in there. We'll see which solutions are good, which solutions are bad. But otherwise we need to write down all the solutions.
Wow.
Yeah. it's a lengthy process. So we do the same for we can maintain c squared greater than 0, but now lambda squared is less than 0. Okay, we can even start from here. R squared is equals to negative c squared squared, like this. So now if c squared is greater than 0 and lambda squared is less than 0, when you multiply them, what type of number are you getting?
We are saying that if they are both greater than 0.
No, check what is on the screen. Saying what?
Okay, so C squared is greater than 0 and then lambda squared is less.
Uh-huh.
So it's going to be a positive number.
Are you sure? With what? C squared. What type of number
So
is c squared in this case?
C squared will be positive.
And
And
lambda.
lambda squared will be negative.
So when you multiply a negative and a positive, what are you going to have?
It will be a negative. Now I was looking at the negative in front there.
Okay, times this negative. So that's, yeah. So, but my question was c squared times lambda squared.
On their own. Okay,
Yeah.
okay.
So it would be
They've
some
given
positive,
that.
yeah. So it would
Yeah.
be some positive number k squared, right? Let me
Yes.
put squared here. So it would be some positive number k squared. So when you take the root of k squared, it will just be plus or minus w. Okay?
Okay.
If we have this value of r, what would be the value of t?
The value of t is going to be, okay, when they are both positive, it's going to be ae raised to the rx, I mean rt.
Oh, okay. wt plus
Then be w2 t.
something like that. Yeah. Very good. Very good. So now we can also do the case for c squared is less than 0. Okay.
Okay.
When squared is less than 0 and r squared is less than 0, what type of number we're going to have? When we multiply
Okay.
we're going to have
So this is negative.
so here it would be a negative, right?
When we put it there, it's going to be a positive because of that negative in front.
No. C squared is less than 0. So what type of number is c squared?
Oh, okay, it will be negative. Okay, yeah. It's going to be negative.
So c squared is negative and lambda squared is negative. When you multiply
Negative, that's
negative
right.
times negative,
It will be a positive.
so positive when you put there,
It will be negative. Okay, okay.
okay, so it will be some sort of this solution again. So we won't write that because it's a repetition. Okay,
Okay.
lucky for
Mhm.
us. Okay, so we can still take c squared less than 0 and lambda squared greater than 0. So it would be more of this form.
Okay, so it's a repetition again.
Yeah, so lucky for us, we don't have to do this case. Okay, so now tell me the 3 solutions that we have of t. I write them down. So the 3 solutions of t that we have, t of t is equals to, the first one was ax plus b. The second one is t of t is equals to
A cos wt
a cos wt
plus B sin wt.
b sine wt. Okay, the other solution,
It was A e raised to the w to the negative wt plus B e raised to the wt.
okay, same applies. Give me the solutions for x, the 3 solutions of x. How many solutions? We have 3 solutions of x, right?
For x, I believe so.
Yeah.
First one was x of x is equals to ax plus b.
Okay, the second one.
The second one was x of x is equals to a cos wx plus b sin wx. Then the third one was x of x is equals to ae raised to the negative wx plus be raised to the wx.
Okay, good. Now we have to pair the values according to the value of r. So for those that when r was equals to 0, I presume it's this first case, right? For both cases, was it r equals to 0?
Yeah.
Then for the second one, was r a complex number, right?
Yes.
Okay, so take this. Then this one is for r that is greater than 0. Okay. Okay. So now remember our solution. So we'll try each of these solutions. So remember our solution, u of x comma t is equals to t of t times x of x. Okay, so now we can test out the first one. For r equals to 0, we have u xt equals to be, now before, okay, we are given those initial conditions. Okay, we need to solve for r equals to 0. We have t of t equals to ax plus b, and x of x is equals to ax plus b. Now, what are the initial conditions that we've been given? So we were given these initial conditions here. I want you to say them out for me. So u of 0 is equals to u of l. So u of 0 comma l, is it? X is
I'll
equals
go
to,
back and just copy them.
yeah, just copy the,
I'll copy them. Yes.
yeah, copy the initial conditions. All right, so what are the initial condition and boundary condition?
Okay, so for the initial condition, we have u in the brackets x comma 0 is equals to f of x.
So this is in. initial IC is equals to f of x. Then
For the boundary, we have u in the brackets. In the brackets, 0, comma t is equal to u of L, comma t.
Okay.
Is equals to, okay.
So we can break it down like that. Okay. Now,
Okay.
what does this tell us? Okay. U of 0, comma t is equals to 0. It's more like we'll get u, our given equation, u of x, comma t equals to t of t x of x. So when applying the boundary conditions, we'll put where there is t, we put t, where there is x, we put x. So we see that we'll put u of x, comma 0 will be equals to t of 0, okay, multiplied by x of what? X of 0.
0. Okay.
Oh, sorry, x of x.
Oh, because the side where there is t, they have replaced with a 0. Okay.
Yeah. Okay. This is for the initial condition. So what is this telling us? Let's compute t of 0. We put, actually this should be t. When we put 0 where there is t, we're just going to have some constant b. Okay. Then now for x of x, we'll come to this